Today I will talk about algorithmic skeletons and algorithmic skeleton composition and manipulation. So I guess most of you saw the keynote yesterday, and in the keynote we saw a quicksort, and Gabriele Keller was talking about how you would parallelize this in Accelerate, or you could do it in FUTAG, or in Accelerate you would look at the filter or at the map, and you would think about, okay, how can I make the filter and the map do optimization with the compiler, whatever. And a different approach is to this is algorithmic skeletons. And the idea behind algorithmic skeletons is that you find common patterns in your code that you want to parallelize, and you put all the additional complexity of the parallelization into the skeleton. So in the best case, the user can just use it as a drop-in replacement. So we have, for example, a map or different maps, a farm, a work pool, or MapReduce or divide and conquer, but also communication like pipeline or a torus. So for this example from yesterday, the algorithmic would to identify a divide and conquer scheme and then just put it into it. And then you can choose, in the best case, from a skeleton library, a good algorithmic skeleton that would fit your hardware or your situation or the specific problem, depending on the data you have. So in Eden, we have a general purpose parallel programming language with explicit process placement. So, for example, a little bit to FUTAG, what we heard before, where we have data parallelism. Here we have explicit process instantiation, like in Erlang, and we have explicit or semi-explicit placement of the and we have a distributed memory model, and it comes with a skeleton library. So for the introduction example, in the best case, you just choose from the Eden skeleton library a good skeleton, and maybe you have to add a few parameters to, for example, control the granularity of the parallel program, or that you don't have too much parallel processes or something like this. When I said explicit or semi-explicit parallel placement, I meant that you have no argument and then now place round robin. For example, we can define a parallel map, and if you map a function over a list, every element of the list is computed on the next processor element round robin. Or there are skeletons where the first argument is a placement, just a traversable of places where the computation should be placed. Now, there are some problems if you want to compose skeletons. With Eden, you have the problem that, for example, you want to write your code as a skeleton composition. So you write the first skeleton, the next skeleton, but you find out that your data is scattered and gathered again and scattered again and gathered again. So you have a lot of unnecessarily intermediate communication, and you need to get rid of this, like, for example, what you would try to do with a fusion. And the Eden solution to this problem is a concept called remote data. Remote data works in the way that you create a lightweight handle to your data. So the idea is that the data itself is heavy-weighted, and you create a lightweight handle and communicate just the handle. And when you instantiate the next skeleton, you give the skeleton just the handle, and it collects the data from where it is. So in the best case, you just have a good locality. So this is the status quo. We have some static placements like cycle, like block, and we have remote data that really helps with skeleton composition, it's just like the distributed interface to composition. And we have some auxiliary functions for granularity control, like chunking or something like this. So, if, for example, if you want to parallelize a map, you would do something like chunk the list and then map a sequential map to control the granularity. But now we want to do some more. And the first thing I did was an idea of a colleague of mine, and he had the idea to tag the remote data with the place where the data is located. So if you have the handle, you also know where the data is without fetching the data. And now you can now you know where your data is, and you can do, for example, co-allocation. You can write a map and say, okay, I want the computation to follow the data, not vice versa. So if you have already distributed data, just bring the computation to the data. This goes easily, but it's not enough. Turns out it's not enough. A simple example, we have an iteration of a map, and there's a function. We don't need to know what this function does, and we have a map. And if we want to do a drop-in replacement, we hope for to be the solution to just have a parallel map and the wrapping inside the remote data structure. But what if the element, the input of the remote data we put into is not distributed quite equally? One idea could be to redistribute it. Or what if the function we are mapping does not depend, or the best placement we can choose doesn't depend on remote data, but rather on more than one. So, for example, the simple case is you have a matrix, and you can co-locate the data of the matrix. A more complex situation. If you have a list function that you want to choose one of the places of the elements in the list regarding the other list. So, for example, first case, you have not good distributed data and want to redistribute it, or you have a situation where you want to redistribute data always with the cost of communication in mind. So you want to get as much parallelity you can get without, with the lowest cost you can get. So what I did is to change the interface of the skeleton library, because with the skeleton library as it was, you could not do something like this. So what and skeletons are only useful if you can use them. So if you have to write a new skeleton every time you have a new problem, you get stuck. In the best case, the person who writes the algorithmic skeleton knows way more about the program than you, and you can't start to, oh, I want a different mapping. I have to look up the skeleton and rewrite it. So the change is to put the actual placement, meaning the communicational structure of the algorithm, as an argument to the skeleton. So, for example, the iterated map we've seen a few slides back, it is actually a Bytonic sort, so we can express it as a nested divide and conquer scheme. And I guarantee you it's really painful if you try to think about the actual communication you need, but it's easy to think about it from a point of view where you know you get an input with an actual placement and you have to choose a placement in this stage. And the good thing is you can just give it to the skeleton and the skeleton will work. And you can different skeletons. You don't have to get too deep into this. It's just or a different scenario, I do some of my testing in Edinburgh, and there's a cluster with 23 computers and 8 cores each. And think of the situation. You want to, for example, you want to compute a rainbow table. You have cryptographic hash functions, and the computation of the hash function is highly irregular. So maybe the best first step is to take a work pool. Then you have your data distributed on 23 computers with the situation that you have communication from one core to another on a computer is much cheaper than the communication between the computers. So maybe the next step is you want to do a sort on the computers itself, and then, for example, with the sorting network, you can do an end-to-end sort and have a distributed result on every computer. You can't express something like that with the old algorithmic skeletons. But you can easily do if you can pass the placement function to the skeleton, because actually this placement function is just a function. So you can not only do dynamic placement, you also can do architecture awareness. You can say, okay, this is a metric and this is a cost function, and do your communication regarding the cost function. Or you can do work pulling and work pushing. This is actually an idea I got from a question from you, because think about it, if you have the first stage is a work pool, you get directly into the problem that the output of the work pool might not be where you expect it to be. Yeah? So you have to catch up after the work pool if your first stage distributes the data irregularly, and the last stage should have the data distributed regularly. All you need is a function that gets an input, and you have a specific output. So you are happy if you can define a function. Okay. There are some approaches I want to compare to really fast. One approach is domain maps. One language that does that is Chapel, and they can define something like an iterator over a distributed domain. But many of these languages, they plan to, but they can't do dynamic domain mapping. They just have blocks and cycles. So from the idea here, it's close to domain maps, but you're more free to go because you have a function. You can just put in every function, not a static one. Or another thing you could do is something like alignment. You can say, I want this remote data connected to this and connected to this, and then in the end, just unroll it and compute a good placement. Just a little bit about evaluation. This is the introductory example with the DisDC skeleton from the Eden library, and with a placement function that optimizes the communication. And the placed graph is the optimized version repeated without the skeleton, because I wanted to know, okay, if I fetch the place of the data every time and compute the location, this is some kind of computational overhead. If I already know the placement, that must be faster, but turns out for the problems we usually solve, the additional overhead is just inside the normal noise of the runtime. And it's, of course, non-surprisingly, really faster than the old skeleton, because you can highly optimize it to a specific placement. So truth is, this might not be useful for every case. If I was programming in FUTAG, I would say, okay, this is not really interesting because I have overhead. I guess if I have something like highly parallel data problems, this might not work. So I guess it's only useful if you need explicit placement or if you want explicit placement. And the more expensive the communication get, the better it is. For example, when you do distributed parallel computing, you always fight against the garbage collector and paging. So if you know you can control the amount of data on every node, you can reduce the risk of paging. And you can control it with explicit placement. The overhead is justified in our case. In others, it might be not. And you get much, much, much more flexible skeletons. And it is a big win, because every time you try to use a skeleton library and there is no skeleton you can use, you're done. You stop using the skeleton library. And you can easily change between control and data parallelism. For example, if I were trying to highly optimize a program, I would think about, okay, maybe the inner stage I would do with some highly optimized functions from Accelerate or FUTAG, and the outer control I can easily do with something like this. And I control the control parallel part I can control with explicit placements. You get obviously nestings because you always have the relative position of the data. You can combine work pulling and work pushing, and I think this is a big plus, because you can't do that so often in other environments. Architecture awareness and cost functions. And what I'm doing right now is writing a bigger skeleton library. I want to do some alignment. And I think you could easily write something like a strategy brewer, where you say, okay, I have this, this hardware, give me a good strategy.